line for the third particle, and the third particle will have the x31. So it will cancel with some terms down here in the dot dot. Same with, so F2n here has Fn2 down here. F23 will have a term on the line of third particle called F32. So it also cancels, and so does all the other terms. There will be a line at the n-1 particle that is Fn-1 and n. So at the end of the day, all the internal forces will cancel when you add them together due to Newton's third law. So what we left here, we are left with the sum of all the external forces acting on the system. These are all forces acting on different particles, but if you look at the entire system, these are the sum of the forces that comes from outside the system. And the sum of it will equal to a sum of, we're seeing, it is the sum of their particles' masses times their acceleration. Okay. So you can see vector is very useful. If we do not have vector notation, I have to do this twice, one for x, one for y. So in practical calculation, vector, you have to break vector into its components, but if you are doing like general proofs, vector is very useful. So the left-hand side is just the sum of external force, and let's call it just Fex. Fex is the sum of all the external forces acting on the system. Is the external force acting on particle 1 plus those acting on particle 2 until you add it to the external force acting on particle n. And for this big thing, we are going to make it even bigger because we don't really know the individual mass of a system macroscopically. Macroscopically, I know the mass of my bottle, but if you ask me what is the mass of the third particle inside my bottle, I have no idea. So we're going to combine all the masses by adding them. I'm going to multiply this thing by the sum of all the masses in the system. But if I multiply it, I need to divide it so that the equation can hold. And the denominator is just what I had before. Yes, Pablo.
Sorry, can you explain why you did that again?
Why I did this?
Yeah.
You'll see. You'll see right now, because now this thing is the total mass of the system. And this fat thing can just be defined as the acceleration of the center of mass. So combine left hand side equals to right hand side, you get back F equals ma. But now the force is not the sum of force on one particle, but the sum of external force on a system. The mass will be the total mass of the entire system, and the problem is this ACN. So what exactly is this ACN? It's going to be the acceleration of something called center of mass. And ACN is defined by, let me write down the definition. ACN defined by the sum of the acceleration of each particle weighted by their mass. So if their mass is bigger, their acceleration becomes more important. And you need to divide it by the total mass, so the dimension is still the dimension of the acceleration. So what is this thing? I claim that if you define something, some position, called the position of center of mass, and define it by the sum of the position of the particles inside your system, divided by the total mass of the system, I claim that that acceleration will be the acceleration of this point. Why do we look at this point? Let's do a simple example. If we have two particles in our system, one heavier, one lighter, then there's only two particles, and we'll only have two terms. Let's say we only have two particles, like this. And to compute it, let's put it on the x-axis. So let's go to the frame of the first particle. The first particle is at the origin, and the second particle is somewhere around here. So to use a vector equation, we break it down into two. The x component of that equation means the x position of the center of mass is m1 times the x position of that particle plus m2 times the x position of the second particle. And because we only have two particles, so we're done. And divide by the total mass. Similarly, the y position of the center of mass will be the sum of the y position weighted by the mass of the particles. Now, because I choose this frame, the y position of both particles is 0. So I get a 0 here. Okay? And for the x position of the center of mass, let me point out that this distance will be the x position of m2. This is where the x position of m2 is. So the distance here will be x2. Okay. Now, the first particle is at the origin. So x1 is, the first particle is at the origin. So what is the x position of the first particle? Good. So you have a 0 here plus m2 times x2. So you get the x position of the center of mass will be m2 divided by the sum of their mass times the position of the second particle. Now, this is just a ratio. This is a number. Is this number bigger than 0 or is this number bigger than 1 or smaller than 1? Smaller than 1, right? The denominator is always bigger than the denominator, so it is something like 1 over 2 or something. So we know the x position of the center of mass will be closer than the x position of the second particle. So this is where the center of mass is. The distance is m2 over m1 plus m2 times x2. Now, if m2 is bigger, we're looking at this. If m2 becomes bigger, will the center of mass, will this distance get longer or shorter if m2 is bigger? If m2 is bigger, will this term be bigger or smaller?
Smaller.
So there's divided, but there's also a denominator. Let's say M2 is so big, then this term, M1 plus M2, is basically just M2. So it's 1. If the mass of the second particle is super big, the center of mass will just move to where the second particle is. So it's like if you remove this ball, because its mass is negligible, if this mass is so much bigger than the other mass, then the center of mass will be at here. So the center of mass will be where the mass is concentrated in the system. We can do it in another way. If M1 is super big, then this term will give you what? If M1 is super big. The denominator will be super big. What do you get if you divide a number by infinity? What is 1 divided by a billion? How about a billion? 0. Good. It goes to 0. So if M1 is super heavy, the center of mass will be right here at M1. If they are the same, then this term, let's replace M1 with M2. Then you have M2 plus M2 divided being M2. That's 1 over 2. If the mass is equal, the center of mass will be right in the middle. So you see why is the center of mass important? Because it's basically where the system is. If it's too rough,